Welcome back to part two of the geometry notes. This is where we left off. We had talked about meshes, we had talked about booleans, we had talked about curves, we had talked about surfaces. Let's see what else we can do. This is something that for some reason is called metaballs. I have no idea why. If you want to play with this, it's in Blender. It's kind of cool. Basically, it's blobbies. That's really what I would call them. Why call them metaballs when you could call them blobbies or even metablobbies? They are blobbies. But the interesting characteristic they have is if you get them close to each other, close enough, the blobbies merge. And so you can make bigger blobbies out of smaller blobbies, and they just gradually merge into each other. I've used this before to create kind of molecule looking things. Molecules really aren't plastic ping pong balls connected with sticks. They really are probabilistic electron clouds, and they blend into each other. The electron clouds sort of blend, and you can do things like that very nicely with metaballs. You can also turn them into meshes too. Here we've said, oh, we have it the way we want it, now make it a mesh, and that lets you pull on points and sculpt it, 3D print it, all kinds of things. You can also model geometry with voxels. This was one of my grad students' research project a few years ago, and he didn't model with voxels. Oh, voxels are these little cubes, in the same way that a pixel is a picture element, a voxel is a volume element. And so he had come up with a way of taking a triangle defined object, a mesh, and turning it into these voxels. A lot of these voxels kind of looks like something you'd see at Legoland. But it's kind of neat. In some ways it's like Minecraft. It's like the way they model 3D geometry in Minecraft. You can combine textures. So here's our friend the sphere. We're going to let this be the moon. Here is the moon's image texture. Thank you, NASA, for making these available. Here is the moon's displacement texture. In some ways, this is like the grayscale image we saw when we talked about shadows. Okay, the variation in the colors is really the height. And NASA gets these by having spacecraft orbit the moon and bounce radar signals off the moon. Well, what's kind of fun is if you texture map the image texture, but then you use this to displace the vertices, which you can do very nicely in a vertex shader. Vertex shaders can read textures just like fragment shaders can. And so when you've got a vertex in the vertex shader, you just read its corresponding position from the displacement texture, and you move the vertex up or down depending on what that displacement texture tells you. And so you get something like this. This is better looking if it's moving because you can kind of get a sense of where the hills and valleys are. But here on the silhouette edge, yeah, you can see that there's edges of a crater. So anyway, this is something special you can do because if you've got both pieces of information here and here, you can end up getting something like this. And here's how you do it. Here's the vertex shader. You've got a sampler. That's the displacement image. Notice the picture image doesn't even come into play in the vertex shader. It shows up over in the fragment shader. We grab the displacement. There's only one thing in it, so it's sitting on the .r. And we take the vertex and we take the displacement we got from that texture and we apply the displacement amount along the normal vector that is sticking out perpendicular to the surface. And then there we go. This now becomes the position that we send down the rest of the pipeline. So yeah, pretty straightforward to do. Fragment shader just looks it up in the color or in the image texture. This is one I thought you'd really like. This is something called L systems. I don't know if you've ever kind of looked into fractals. This is something you may have run into. It's called an L system because, well, because of the L of the last name of the person who invented it. But basically, he came up with a little language. You've seen turtle programs that do this. But anyway, F means move forward, plus means move or rotate to the right, minus means rotate to the left. The square brackets mean push and pop. Push the current location, and then over here, pop the current location. That's how we go up, stop, come back to here, and continue on. If we didn't have the push and pops, we would have to, well, I don't think we could do things that forked like that. So anyway, what's fun with this is what if for all the F's I have in this object, what if I take every F and replace it with this entire equation and except make each F in the entire equation smaller? Well, I get this. If I do it once, well, I get that. But if I take every F and turn it into the whole equation, you can see, well, look at this. This is the whole equation, and it's replacing what used to be one straight line. This is taking it 2 deep. This is taking it 3 deep, 4, 5, and all of a sudden, from some basic shape that looked like a kind of a skewed tuning fork, we have a reasonably convincing bush. Now, it's a 2D bush because this equation only works in 2D, but of course we could add other things to the vocabulary, like maybe up arrows and down arrows mean tip up and down. These greater than less than mean tip left and right, and then all of a sudden we can make a 3D bush out of this. So this is called an L system, and there's a lot of things that can be modeled this way, but it's really fun because you can get a lot of different shapes like this by just doing a slight manipulation to the equation. Of course, modeling can feed simulations. Here's an explosion. Kaboom! Exploding monkey. We'll talk about 3D printing in more depth, but I wanted to mention it just a little bit here while we're doing about geometric modeling. One of the biggest things in 3D printing that causes 3D printers to screw up is the object must be a legal solid. There must be a definite inside and outside. Meaning if I have a sphere and I eliminate this face, it is no longer a legal solid. That is, it's ambiguous. Where is the inside? Where is the outside? Because, well, out here is connected to in there. So how can one be inside and one be outside? Or legal solid is what I call it. Sometimes people use the phrase two manifold or watertight, but you get the idea. And there's a nice equation. There's something called Euler's formula, and Euler's formula for a legal solid, a simple legal solid, is faces minus edges plus vertices equals 2. Well, for a cube, faces minus edges plus vertices equals 2. That's the simplified version of the formula. This is the full version of the formula. This one's easier to just remember. But L is loops, so if you have just a loop of points in a surface, you get an L. B is the number of bodies, so if I have 2 cubes here, the number of bodies will be 2. Genus are the number of holes. See, this is just a loop, but if I put a loop on the other side and connect them through, then that's now a through hole, a G. But anyway, a useful formula because you can pretty much tell right away if something's a legal solid by do these numbers actually add up to what they're supposed to add up to? Well, I mentioned about using unions to help you with the 3D printing. The OSU library currently has 4 3D printers that students can get access to. And when they first got them, they were curious about how bad can you make your 3D models and have them still work. And so they called me and they said, "Can you put together bad things?" And I said, "Oh gosh, I can surely put together bad things. I've been doing that my whole life, mostly by mistake." So I did exactly what we talked about before. I took a cylinder and a cube and overlapped them. That's illegal. Things in real life cannot occupy the same space. Then I took the Boolean union of that and got this. And you can see that the cylinder ends here, the cylinder ends there. There's nothing that occupies that middle space. Well, surprisingly, the 3D printers did a good job. If I took this bad one and when I printed it, it was wrong, but it wasn't wrong in a horrible way. That is, it didn't start spewing plastic all over the plate. And here's what it did when I did it right. And yeah, that's what it was supposed to do. So anyway, some amount of knowledge of geometric modeling does come in handy in other things like attempting to deliberately screw up a 3D printer.